Hello students, today we will be seeing relations and functions theory part. And before jumping into our this session, there's a small disclaimer. The images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the same. Thank you. So, first of all, let's have some basic idea about how these units, chapters divided according to marks in board exams. So, first, this relation and functions uh, co- consist relations and function ITF consist 8 marks. Algebra, matrices, determinants 10 marks. Calculus, continuity, differentiability, integrals, derivatives, application of derivatives 35 marks. 3D vector 14 marks, linear programming 5 marks and probability just 8 marks. So you just have seen that the main part is calculus part. Now what about the other remaining 20 marks? So theory of will be of 18 marks. Now the 20 remaining marks will be given by the internal assessments, the periodic test and math activities depending on your school. Clear? Now here's some analysis of recent JEE main exams, weightage according to the chapters, units, and just combining all the previous shifts of JEE mains. So, relation and function ITF, considering ITF in it, 27 number of questions, matrices determinant 20 questions, continuity and differentiability 16 question, application of derivative differential equation 22 questions, integrals application of it 35 questions, vectors 3D 40 questions, probability 11 questions. So these are some analysis of just previous shifts of mains. Clear? Now what we will be covering here is very important. So we will be recalling some important things which will be required in this section for this chapter, relation and function. Then relation definition, relation representation, number of relations from a set to another set, types of relations, equivalence classes, what do we mean by that? Questions, we will be seeing some questions based on this theory through which we can recall, memorize or see that how we grab the theory. So let's see the first point. So recalling some basic concepts. So Cartesian product. So you must know about the Cartesian product of sets. So given two non-empty sets P and Q, the Cartesian product is simply denoted by P cross Q is your set of all ordered pairs of elements from P and Q. Meaning simply F cross Q is collection of all ordered pair PQ such that P belongs to set P and Q belongs to set Q. Simple. And what do we mean by ordered pair? This ordered pair must be very important term here. So suppose P1 Q1 is some pair in this P cross Q and P2 Q2 is another pair. If both are same, so what do we mean by both pairs are same? Which only going to happen when P1 is same as P2 and Q1 is same as Q2. The corresponding part of this pair must be same. Clear? If either, if either of your P and Q is null or empty set, then we describe P cross Q as phi set, empty set. Clear? So this is the basic idea of Cartesian product. Now relation. If there are p elements in A set and q elements in B set, then there will be pq elements in Cartesian product of A cross B. Meaning simply, so Na represent the number of element in set A, P, and B represent the number of elements in set B, Q. So total number in the set Cartesian product A cross B is going to be PQ. Simple. By the very definition, you can verify that. So in definition, if you observe that you are going to have pairs A comma B, where A belongs to set A, B belongs to set B, and how many pairs you can form? Very simple. For first element of the pair, you will be having P choices, and for second position of the pair, you will be having Q choices, as first must belongs to set A and second must belongs to set B. So in total, you will have P cross Q choices or pairs. Simple. Now, a relation. So a relation in mathematics defines relationship between two different sets. So in daily life, the meaning is also the same. In mathematics, the same. Okay, it just simply defines some relationship between two different sets. And a relation in maths is a subset of the Cartesian product of the given two sets in which we are talking about. You will be seeing as we go through deep in this session or in upcoming lectures, you will be seeing that what do we mean by this relation and what do we mean by the subset as Cartesian product. Now a relation R from a non-empty set A to non-empty set B is a subset of the Cartesian product A cross B. The subset is derived by describing a relationship between the first element and the second element of the ordered pairs in A cross B. So subset is simply, so first of all, your relation must be of a subset. Your relation must be a subset of the Cartesian product A cross B. And the relationship between A element and B element of the pair must be derived by describing the relationship between the first and the second element simply. If it is not clear, be with us. It will be clear in upcoming slides when you are going to see some examples related to relation. So the second element is called the image of the first element. So you are having your pair A comma B, so the second element, which is B, will be calling we will be calling it as the image of the first element. So these are the some terminologies we are going to use or generally used in this chapter, relations and functions. Now the set of all the first element of the ordered pairs in a relation R from a set A to set B called the domain of the relation R. So domain of any relation R is simply collection of all first elements of the ordered pair in the relation. Simple. So if you are having your relation, your subset of A cross B, collect all your first elements members and make a set out of it, and that set will be your domain of the relation. Simple. The set of second elements of the relation R from A to B is simply your range of the relation. Simple. And the whole set B, so this set B will be your codomain of the relation. Please pay attention to these terminologies. These are very important for this chapter, relation and function. Especially in functions, we will be talking about domain and range in functions frequently. Now, as we just saw, the range, by the very definition, the range is going to be the subset of codomain set. As range is just a set of collection of all the second elements, and those second elements belongs to what? belongs to the set B, which is your codomain. Simple. So just by definition, but very important point. Now, a relation may be represented algebraically either by roster method or by set builder method. So you have two methods, so by which you represents your sets or relation roster and set builder. Second point, an arrow diagram is a visual representation of a relation. So for example, here you are having your A set, B set, your relation A to B, and you are having your relation defined as that, or pairs in your relation as 2 comma 2, 2 6, 2 8, 3 6, 4 8, and this all represented by this arrow diagram showing that 2 is related to 2, 6, 8, 3 only related to 6, and 4 only related to 8. So this is your arrow diagram representation. And roster form, you will write 2 2, 2 6, 2 8, 3 6, 4 8. Clear? This is your domain set of your relation R. This is your codomain set, and all related elements from this codomain set will be your range set. So here, especially this case is your where range set is same as your codomain set. Clear? Now, total number of relation. How you are going to find out the total number of relation? Very simple. From a set A to set B, the number of possible subsets of A cross B will be your total number of relations. Simple. So if you are having first set with cardinality P, second set with total number of elements Q, then we know that the number of elements in A cross B will be PQ, and the subset number of total subsets of this set having total elements PQ is simply given by 2 raised to power PQ, and this is same as saying total number of relations. Clear? If you recall, what do we mean by relation? So relation from the definition is just a subset of your Cartesian product A cross B. So you can form how many subsets? 2 raised to power PQ. Simple. So far so good. Now let's see different types of relations. So first, empty relation. What do we mean by empty relation? So R in a set A, meaning if such thing is given, there is a relation R in a set A, meaning we are having domain set and codomain set as same, meaning we are going to have our relation R subset of A cross A, Cartesian product. Simple. So empty relation is simply if no element of A is related to any element of A. So R is simply empty relation in which we are going to have no element of A related to any element of A. Simple. Empty relation. Clear? Now a relation, universal relation. So a relation R in a set A, meaning subset of A cross A, if each element A is related to every element of A. So each element of this domain set A is going to be related to every element of A. Simple. So your universal relation. Clear? In this case, so your R will be simply A cross A set. Clear? Now, reflexive relation. So we say that the given relation is reflexive when A comma A pair must belongs to the relation R for every A of this code. Every A belongs to the domain set. Simple. Symmetric. If this pair A1 comma A2 belongs to the relation R, if this pair belongs to R, then we are going to verify that if you reverse the order, like this A2 comma A1, and verify that this pair belongs to R. If this is going to happen for every pair A comma 1, A1 comma A2 belongs to R, then you will say that your relation is symmetric. In simple words, if you are having a pair A1 comma A2 belongs to R, then you have to see that the reverse order pair also belongs to R. If it does, then it is your symmetric. If it does not satisfy the condition, then it is not symmetric. It will be all clear when you see some examples. Now transitive, if two pairs belongs to R, like A1 A2, and next pair will be starting from this A2 A3, then your third pair must belongs to R also, A1 comma A3. A1 comma A3. So this is your transitive property of the relation, not property, meaning transitive relation. So if such condition is satisfying, then you will say that your relation is transitive. A relation R in a set A is said to be equivalence relation if all these three satisfied. If your relation is reflexive, symmetric as well as transitive. Clear? Now, this example. So, T be the set of all triangles in a plane with R a relation in T given by R, this collection of all pairs T1 comma T2 such that T1 is congruent to T2. Show that R is an equivalence relation. So, in order to show the given relation equivalence, we need to show that R is symmetric, transitive as well as reflexive. So, solution. So, starting with the conditions of equivalence relation. So, reflexive. We know since every triangle is congruent to itself, so by definition T1 comma, so from the first sentence you will get by definition T1 comma T1 belongs to R. Clear? Now from this second sentence, if T1 comma T2 belongs to R, meaning T1 is congruent to T2. So in second condition, we always start with the given thing or assuming that it is already given to us. So we are assuming that this pair belongs to R. Now we have to show that T2 comma T1 also belongs to R. So by definition T1 comma T2 gives me T1 is congruent to T2. Now T2 is also congruent to T1. The same thing. If T1 is congruent to T2 is the same thing as saying T2 is congruent to T1. But in pair form, we are going to write it as T2 comma T1. And now you are seeing that if this going to happen, then this will also going to be happen. So by definition, it is your symmetric relation. So R is symmetric. Moreover, assuming T1 comma T2, T2 comma T3 belongs to the relation R. So always start with the transitivity starting with two pairs taken in this form T1 comma T2 and another pair with starting with the second element of the first pair. So T2 comma T3 belongs to R. Now we have to show that T1 comma T3 belongs to R. So now first of all, we are trying to get the points out from this pairs. So what we are getting is T1 is congruent to T2 from first pair and from second T2 is congruent to T3. Simple. Now as T1 congruent to T2 and T2 is congruent to T3, we can directly see the congruency going to be transferred. So T1 is congruent to T3. So T1 congruent to T3 giving me T1 comma T3 pair belongs to R. So by definition, we are having R is transitive. So far we have seen R is symmetric, sorry, R is reflexive, R is symmetric, R is transitive. So our given R is equivalence relation. Clear? I hope it is clear. So when you start, so when you see, every time when you see your question related to reflexive, symmetric, transitivity, always start with the given condition. For symmetric, you have to show T1 comma T1 always belongs to R, for T1 belongs to the domain set, or in general A1 comma B, A1 comma A1 always belongs to the relation R, for A belongs to the domain set. If A comma B pair belongs to R, then always show B comma A also belongs to R in order to show symmetric. For transitivity, start with A comma B and B comma C pair belongs to R, and then show A comma C belongs to R. Moving on to next. Another example. Let L be the set of all lines in a plane and R be the relation in L defined as, so R is your relation R, collection of all L1 comma L2 pair such that L1 is perpendicular to L2, and show that R is symmetric but neither reflexive nor transitive. Simple. Solution. So starting with the conditions. So for reflexivity, we have to show, so always start with reflexive property, reflexive relation to show. So what we have to show is L1 comma L2 belongs to R. If it does, then it is reflexive. If it doesn't, it is not reflexive. So by condition L1, so in order to L1 comma L1 belongs to the relation R, we must have L1 perpendicular to itself L1. But we know that any line cannot be perpendicular to itself. So by this condition is not satisfied. So L1 comma L1, this pair does not belongs to the relation R. So not reflexive. Now for symmetricity, if L1 comma L2 belongs to R, so for symmetric relation, we always start with a pair belongs to R. Always start with this. Now from this, what we can analyze is simply that L1 must be perpendicular to L2 by the very definition of the relation set. So L1 is perpendicular to L2. Now this is the same thing as saying L2 is perpendicular to L1. Same information but different words. And these words led to me and forcing me to write L2 comma L1 pair belongs to R. Yes? Why? Because if L1 comma L1 is perpendicular to L2, then I can write L1 comma L2 belongs to R. So this is the same case here. L2 is perpendicular to L1. So this condition enforcing me to write a pair which is saying L2 comma L1, and this condition also enforcing me to write that this pair belongs to the relation R. Clear? Now what about transitivity? Very simple. So R is not transitive. Why? Let's see. So always as I have said that always start transitivity with two pairs L1 comma L2 and L2 comma L3. So if both belongs to the relation R, meaning L1 is perpendicular to L2 and L2 is perpendicular to L3, so then L1 can never be perpendicular to L3. You can easily assume. So assume two lines perpendicular to each other, name them L1, L2. Make another line perpendicular to L2 and name it L3. You can easily observe that line not going to be perpendicular with first line L1. So not transitive. In fact, L1 is parallel to L3. If you try to draw your diagram, the rough representation what is happening, you will see that L1 is parallel to L3. Clear? So what so we started with L1 L2 belongs to R, L2 L3 belongs to R, but we have concluded that L1 L3 doesn't belongs to R, so not transitive. So far so good. Now another example, show that the relation R in the set 1 2 3 given by, so relation R is simply in roster form, so pairs 1 comma 1 2 comma 2 3 comma 3 1 comma 2 2 comma 3, and this relation is reflexive but neither symmetric nor transitive. Now here you can easily answer the question, as your relation is given in symmetric in roster form. Solution. So starting with the given information, so for reflexive what we need is, so first of all your start with your domain set which is 1 2 3 and see that for domain elements are you getting the pairs 1 comma 1 2 comma 2 and 3 comma 3. For each element always see that if A belongs to the domain set, then A comma A must belongs to the relation R. If for all elements it is happening, then your relation is reflexive. So as you can see, we are having three elements 1 2 3 and we are having pairs 1 1 2 2 3 3. So it is reflexive. So by the definition it is reflexive. Now for symmetric, we always start with the element in this set, in relation set, not with this set. In reflection we start with domain set. Now just try to see that for any pair, or you can see for each pair you must have pair of opposite order, meaning if you are having 1 comma 1, then you, if you reverse the order, that pair must also belongs to the relation R. So if you reverse the order, you are getting the same element, so same goes for these, but in this case you know 1 comma 2 belongs to R already given to you. If you interchange the position, you will get another pair which is 2 comma 1, and you are seeing that there is no element 2 comma 1 pair, so not reflexive. So 1 comma 2 belongs to R, but 2 comma 1 doesn't belongs to R, so not symmetric. Now for transitivity, always pick two pairs such that first pair 1 comma 2 for example here, and the second pair must be of such form that the first element of the second pair must be same as the second element of the first pair. So in this case 2. So we are seeing that 1 comma 2 belongs to R, 2 comma 3 belongs to R, while 1 comma 3 does not belongs to R. So not transitive. I hope this is clear to you. Moving on to next. This example. So show that the relation R in the set of integers given by, so your relation R is collection of all pair A comma B such that 2 divides A minus B. So A comma B will be those pairs where this difference A minus B divided by 2. Now we have to show the given relation is your equivalence relation. Very simple. Just what you have to show is your given relation is reflexive, symmetric, transitive. So solution. So solution starting with reflexive. So what you need to show is simply A comma A pair must belongs to the relation R. So let's see. So if A comma A belongs to the relation R, how we are going to show the A comma A pair belongs to R? If the difference A comma A is going to be divided by 2, then you can easily say that your pair belongs to R. Simple. So you know A minus A So starting with a minus a, which is 0, and indeed 0 is divisible by 2. So by the definition, we can say that your relation R is reflexive. Therefore 2 divides. Now for symmetric part, we always start with a comma b pair belongs to R. So starting with a comma b belongs to R. If it belongs to R, meaning it satisfies the condition. So 2 divides a minus b. Now what we have to show is b comma a belongs to R. So if 2 divides a minus b, then 2 also divides b minus a. It doesn't matter. If you reverse the order in subtraction, it still divides, it still is divisible by 2. The only difference is the answer, the quotient will be different. Here there is no relevance for quotient. We just requiring the divisibility condition, and it is fulfilling here. Hence what we are getting is b comma a belongs to R. So symmetric. Similarly, for transitivity, starting with 2 pairs belongs to R. So a comma b belongs to R, b comma c belongs to R, and need to show that a comma c belongs to R, meaning a minus c must be divisible by 2. Let's see. So for from first pair, we are getting a minus b is divisible by 2, and from second pair, b minus c divisible by 2. So we can write a minus c as sum of a minus b and b minus c, which is, if you try to see what is happening here is a minus c. Yes, and this is nothing but even number. So if a minus c is your some even number, meaning a minus c will be your 2 times some integer, meaning a minus c divisible by 2. So R is transitive. Thus R is your equivalence relation in Z. I hope it is clear. Now this example, let R be the relation defined in the set A. Set A is elements 1, 2, 3, 4, 5, 6, 7. Relation R is simply defined by collection of all pair A comma B such that both A and B are either odd or even. Show that R is your equivalence relation. Further, show that all the elements of the subset 1, 3, 5, 7 are related to each other, and all the elements of the subset 2, 4, 6 are related to each other. But no elements of the subset 1, 3, 5, 7 is related to any element of the subset 2, 4, 6. Simple. So first task for you is to show your given relation is your equivalence relation. So solution, starting with the conditions. So take any element A from the set A, and you know A and A must be either odd or even. Simple. So we are having A comma A belongs to this relation R. So this shows your relation R is reflexive. Now if A comma B belongs to R, meaning by the definition of the relation R that both A and B might be odd or even. So giving me B comma A pair also belongs to R. Simple. Similarly, if A comma B belongs to R and B comma C belongs to R, all elements A, B, C must be either even or odd simultaneously, and forcing me to write this pair A comma C belongs to R. I hope this is clear that how we are getting our reflexive, symmetric and transitive conditions satisfied. So let me just go through once again. So if you start with any A, so you are going to pick A from this set, obviously. Then if you, and you can only pick an element at a time. So if you pick odd element, then a comma a will be your odd comma odd. If you pick even, then it will be even comma even, and by the definition this pair must belongs to R. If a comma b belongs to R, meaning if a is odd, then b must be odd by the definition. If a is even, then b must be even. So we can also write b comma a belongs to R, and same goes for transitivity. Moving on to next part. So hence R is your equivalence relation. Further, all the elements 1, 3, 5, 7 are related to each other. Why? As all the elements of this subsets are odd. Similarly, all the elements of the subset 2, 4, 6 are even. So they are related to each other. As also no element of the subset 1, 3, 5, 7 can be related to any element of the set 2, 4, 6. As according to the set, we require odd comma odd condition or even comma even condition. So 1 cannot be with 2, or any odd number cannot be with even number. Simple. Clear? Now equivalence class. Given an arbitrary equivalence relation R, in an arbitrary set X, R divides X into mutual disjoint subsets AI called partitions or subdivisions of X. So you are having your relation, equivalence relation R, and a set X, and this relation R divides this given set X into mutually disjoint subsets AI called partitions. So satisfying some conditions. So what? First, all elements of AI are related to each other. Simple. Second, no element of AI is related to any element of AJ where I not equals to J. And third, the union of all AIs or AJs will be your X. Also, the intersection must be phi empty. Clear? So the subsets AIs are called as your equivalence classes. So these AIs will be your equivalence classes. If it is not clear from this simple language, so doesn't worry, we will be seeing an example. So first of all, remark, and this tells us that each element in the set is related to every element in the set. It is clear, much easier to read than listing the ordered pairs of the relation. Simple. So why we are talking about equivalence classes? Because we do not have to rewrite again and again. This simply gives us the clear idea that much easier to read than listing the ordered pairs of the relation. Simple. So we are not going to list all the ordered pairs of the relation. We just have your equivalence class. If your relation is a equivalence relation, then it is very easier to write the equivalence class in order to just get the idea what is happening, what elements is related to each other and what elements are not related to each other. Simple. So if I had to write out all the ordered pairs of these relation, I have to write all pairs. Instead, I can just give the equivalence class. Yes. So clear? So this question. So your A set A comma B comma C. So how many possible relation exist on A? Just explain. Solution. So starting with your A cross A, in order to get the idea about the possible relation on A. So we must have first of all the Cartesian product. So A cross A. And in A cross A, we are going to have how many elements? How many pairs? 9 simply. So we are having 3 choices for first position, 3 choices for second. You can easily observe also that we are getting the 9 pairs: 1, 2, 3, 4, 5, 6, 7, 8, 9. Simple. Now 3 cross 3, total 9 order pairs in A cross A Cartesian product. And the number of relations given by, simply we know the any relation A or R, any relation R or A is a subset of A cross A Cartesian product. So total number is simply given by 2 raised to power n. N represents your number of elements in this set A cross A. So in this case, the number of relation on A is the number of subsets of A cross A. So given by 2 raised to power n. So 2 raised to power n meaning number of possible relations 512. Simple. So they are 512 possible relation on set A. I hope this is clear. This is directly from the theory which we had already covered. Now next question. So this question is related to the terms domain and range. So your R on set A, so you have to find out the difference between domain and range. So solution, very straightforward solution. So as we discussed, domain and range is very simple. So domain is simply of any relation R is the first component, first position, first element of ordered pair. Simple. Collection of all first elements of the ordered pair from the relation R. And range, collection of all second elements of the ordered pair from the relation R. Simple. Clear? So very simple. So just you have to collect all the first elements, and that set will be your domain, and collect all the second elements, and that set will be your range set. Simple. Another question. So is a relation where every element in a set is related to itself consider a reflexive relation or a symmetric relation? Justify. So solution, very simple question, straightforward. So starting with a relation where every element is in a set is related to itself is called reflexive relation. If you recall the definition of reflexive relation, you must have the condition fulfill that A comma A belongs to the relation R, meaning every element from the domain set must belong also related to itself. So a relation R on a set A is reflexive if A belongs to A. For every A belongs to A, this pair A comma A belongs to R, meaning each element is related to itself. So and while the symmetric relations condition is if A comma B belongs to R, if this is happening, then we try to see that is the this pair B comma A also belongs to R. So for symmetric relation, this condition must be satisfied, and these all two conditions are different from each other. So therefore, relation is reflexive, not necessarily symmetric. So this is it from this theory session. Thank you.